So in the last class, we had discussed continuity of a function at a point, continuity of function at endpoints, continuity on an interval, and the kinds of discontinuity. Now, continuity of composite functions, just a short thing. It is not a difficult thing. Continuity of composite functions and continuity properties of continuous functions, these two, and then we move on to differentiability. So continuity of a composite function, just a second. Yeah. So if a function u of f of x is continuous at a point x equal to a, and the function y equal to g of u is continuous at the point u equal to f of a, that means it is like this. This is a function y is equal to g of f of x. Now f of x is continuous at x equal to a, and g of x has to be continuous. See, for this function to be continuous here, for this function to be continuous, f of x must be continuous at x equal to a, and g of x must be continuous at f of a. All right, when x goes to a, so g should be continuous at f of a. Then we say function is continuous. For example, let us try to take a discontinuous function. So let us take a sine of tan x. Sine of tan x. This is a function. Now, in fact, I'll do like this. Sine of pi by 4 tan x. All right. Now, at x equal to pi by 4, at x equal to pi by 4, that is at 45 degree, tan x is continuous. Tan x is equal to 1. It is a continuous function. So this will be, so tan x is continuous. So, and in fact, tan pi by 4 will be equal to 1. All right. So therefore, this function f of x is sine of pi by 4 tan x will be continuous at x equal to pi by 4 because what? Because sine is continuous. Of course, sine is continuous for all, but we will discuss this. Sine is continuous at pi by 4 tan pi by 4, which is pi by 4. Okay. So the answer will, so function value will be 1 upon root 2. So this function f is continuous at x equal to pi by 4. All right. Now consider this case at x equal to pi by 2. At x equal to pi by 2, what happens? We all know how the tan function looks like. We'll expand this. Okay. So there's the tan function. We know that. Now at x equal to pi by 2, so it is 1.57, something close. So something like this. This is the value of, this is pi by 2 here. Now as x approaches pi by 2 from the left, tan x approaches plus infinity. But when x approaches pi by 2 from the right, tan x approaches minus infinity. So function is discontinuous and function is not defined at that point. So at x equal to 2, at x equal to pi by 2, tan x is discontinuous. Therefore, f of x is equal to sine of pi by 4 tan x will also be discontinuous. In fact, it is not even defined, you can say. Same we can do in this way. Just I reverse the example. Let's say f of x is tan of pi by 2 sine x at x equal to pi by 2. At x equal to pi by 2, sine x will be a continuous function. Sine x is a continuous, throughout continuous function. So sine x is defined. However, tan of pi by 2 sine x at x equal to pi by 2. So it will be pi by 2 into 1. So tan will not be continuous. What is the answer for this? Will it be continuous or not?
Discontinuous, no, sir.
Why? What will be the left hand limit and right hand limit? Tell me. I'll define tan x like the function like this. Tan of pi by 2 sine x for x from 0 to 2 pi we will take. Okay, so 0 to 2 pi or 0 to pi. except pi by 2. X not equal to pi by 2. 0 to pi. For x equal to pi by 2, let's say we say it is 1. Now you tell. What is the left hand limit and right hand limit of this function at pi by 2?
Plus infinity, right hand limit is minus infinity.
Okay, left hand limit x tends to pi by 2 minus tan of pi by 2 sin x. This will be tan of pi by 2 into 1. Okay, pi by 2 into 1. Now this number will be greater than 1 or less than 1?
Less than 1.
So this product will be slightly less than pi by 2. So slightly less than pi by 2, you get plus infinity. Now let us look at right hand limit. Limit x tends to pi by 2 plus tan pi by 2 sin x, which is tan of pi by 2 into 1. What? Plus or minus? Value of sin x at pi by 2 plus. It will be 1 plus or 1 minus?
Minus.
Good. Because sine will always be less than 1. So again, this will be plus infinity. Both limits are tending to infinity. But the function value here is defined as 1. So therefore, the function will be discontinuous. And one more thing, you cannot define at exactly x equal to pi by 2, sine x will be exactly equal to 1. So pi by 2 into 1, this will be exactly equal to pi by 2. So tan pi by 2 is undefined. That's why we have to define like this. So this is about composite continuity. You have to see the function within should be continuous and the outer function should be continuous at the function value within. All right. So both. So in the previous case, what we saw was the inside function itself is discontinuous at x equal to pi by 2. In the next example, what we discussed is inside function is continuous throughout, but the outer function is discontinuous. So these you have to be careful in composite functions. We just need to be little thoughtful. Okay. Next, these are important properties of continuous functions. So let f and g be two continuous functions at x equal to a. Then you multiply f with a constant. The function continues to be continuous at x equal to a. All right. Because f and g are continuous, the sum f of x plus g of x will be plus or minus g of x will be continuous at x equal to a. And the product will also be continuous. The ratio f of x over g of x, this will be continuous at a provided g of a is not 0. If g of a is 0, at that point it becomes discontinuous. Okay. Now, next, this part is very simple. all the first four. Then these three are part of what is called as the intermediate value theorem. And these are extremely useful for finding the roots of equations. Okay, they are very roots of equations of any type of functions, not just polynomial or algebraic, any type of functions. They're very useful. So what this property says is if f of x is continuous on AB such that, okay, such that f of A and f of B are of opposite signs, then there exists at least one solution of the equation f of x equal to 0 in the open interval AB. So here we have, let's say, okay, you can have a negative sign also. Now, let's say this is the interval A, B, and f of A, if f of A is positive, f of B is negative. Let's say f of A and f of B are of opposite signs, which means f of A into f of B is negative. Product is negative means they are of opposite signs. Sometimes it is said in this language, in verbal, f of A and f of B are opposite signs, or it is mentioned in this mathematical language, f of A into f of B less than 0. And function is continuous. Because function is continuous, what happens? You have to join these 2 points with a curve without a break. You don't, no matter what the function is, it increases or decreases, but then you, without lifting the pen, we have to join these 2 points, f of A and f of B. This is f of A and f of B. Because the function is continuous, you will have to cross this x-axis, and this curve will necessarily cut x-axis at least at one point, if not more. At least. They can be more also, like this. I will draw. It can cut like this also. So they can be 3 points. In the previous case, there was only 1 point. Here there were 3 points where it cuts. So the thing is, f is continuous. F is continuous on closed interval AB, and f of A and f of B are of opposite signs. Then there exists, the sign is for there exists at least one x belonging to AB such that f of x is equal to 0. So in other words, f of x will have at least one root in AB, in this open interval. F of A is not equal to 0, f of B is not equal to 0. So at closed interval AB is meaningless. In the open interval AB. Okay, this is the intermediate value theorem, which is very useful. Extremely useful theorem for solutions of equations. If you have to identify the solutions, we substitute different values in the function. And if those function values are of opposite sign and the function is continuous, then we know that there will be one root definitely in between them. Now, next, if f of x is continuous function such that f of f maps ab to ab. Okay, this is just an extension of just an extension. Now, this is the domain, and this is same as the codomain. Okay. Okay. So function, graph of the function will exist within this box, within this region bounded by these 4 lines. All right. So now the function is continuous. Now let the function be anything here. One important thing here is it's a continuous function, and of course it's not mentioned, it's onto here, but let's see. Even if it's not onto the entire range, okay, let's say I draw this function, then there will be one point, at least one point, there's the line y equal to x. There'll be at least one point where the function cuts this line y equal to x. So there will be, so here this will be x. This will, because this point is y equal to x, x value and y value will be the same. So we get f of x is equal to x. The function value is equal to itself. Yeah. Because again, it's a property of continuous functions. All right. Now, intermediate mean value theorem, intermediate value theorem is actually a more general statement of the the 5th case. It says if a function is continuous on closed interval ab, then it takes all values, all intermediate values between f of a and f of b on open interval ab. So I'll do this one. So f of a, f of a and b. Let's say this is f of a and this is f of b. Now this is the value of f of a, this is the value of f of b. Okay, what intermediate value theorem says is function is continuous. Okay, so we have to join this point and this point without lifting the pen. Now, no matter what I go, what trajectory I go, I may go outside of this, but we can see all the intermediate values between f of a and f of b. All right, all these values are taken by the function. That is what is the intermediate value theorem. Okay, these are very useful ones to find roots, and also for general aptitude also analysis. It's very useful. So the fifth one, where this particular result, where f of x has at least one root in open interval ab, it's just a consequence of the intermediate value theorem. There, if f of a and f of b are of opposite signs, then f of x, f equal to 0, function value equal to 0 will be one of the intermediate values. Okay, that is about intermediate value theorem. So these are properties, very useful and important properties. Next, we move on to differentiability of a function. So now differentiability at a point, I'll explain. Now differentiability at a point. Let's say we are discussing differentiability of f at x equal to a. So let's take function like this. Okay, now you just look at this. Let's say I'm just consider a curve like this. And I'll try to extend this. Yeah. This is x, this is y. This is a function y equal to f of x. Now let us take some point a here. You look at this, the what I am explaining now. Please pay very careful attention. You will understand differentiability beyond a doubt when I explain at this point. So now this is x equal to a. What is the function value here? F of a. This is f of x, right? F of a. So let us say this point we mark as a. What will be the coordinates of a? It will be a comma f of a. What I do next, I take a point to the right of a, at a distance of small h from a, and I will take another point to the left of a at a distance of small h from a. So these two distances are equal. Now this point, let it be b, and this point, let it be C. Okay. So what will be the coordinates of B? A plus H, comma, f of A plus H. What will be the coordinates of C? A minus H, comma, f of A minus H. Now, what I do, I'll draw a line such that it passes through AB. Okay. Maybe I'll draw a free hand. Okay. I'm just drawing this chord AB and I'm extending this chord. Okay. This is chord AB and I'm extending the chord. It becomes a secant. This is called as the secant. All right. Now AC also I join. I'll get another chord. Now just look at this. What is slope of secant AB? AB. What is slope of AB? Line joining AB. Secant is an extended chord. All right, we know that. So slope of the line joining these 2 points A and B is f of A plus H minus f of A by A plus H minus A, which will be H. What is slope of secant AC? Slope of secant AC, A and C. So we get f of A minus H minus f of A by A minus H minus A, that will be minus H. So now what I do, I make H tend to 0. Now as H tends to 0, H is a positive quantity. All right, remember H is a positive quantity because we took A plus H and A minus H. So H will be a positive quantity. Now as H tends to 0, the point B moves towards A. You see here, this point B moves towards A. Here, this is A, this is C, this is B. Okay. Now as B moves towards A, what happens? This AB touches, AB line just touches the curve at A. Then the secant AB becomes a tangent at A. All right. Also, as H tends to 0, the point C moves towards A similarly, right? As H becomes 0, a minus h comes closer to h, closer to a. So this point C moves towards a. In that case, the secant AC becomes tangent at a. All right. Now, this limit of this slope of the secant AB, limit h tending to 0, the slope of secant AB that is limit h tending to 0, f of a plus h minus f of a by h. This is called as, this is written as f dash a plus, and this is called as the right hand derivative at a. Okay, and it is equal to the slope of the tangent at a, considering the secant to the right of a. All right, the way I explain to the students is like this. So I'll draw a tangent line more carefully. Mhm. So this is the tangent at a. Okay, so the curve, this particular line touches the curve at a at one point. So now when you look at the secant AB as h tends to 0, this AB should merge with this line. All right, and the secant AC, this also should merge with this line. All right, if that happens, so if you get a tangent by taking a and a point just to the right of a and draw a line, you get slope of the tangent at a taken from the right, and it is called as the right hand derivative. And if you take limit of the slope of secant AC, which is limit h tending to 0, f of a minus h minus f of a upon minus h is equal to, this is f dash of a minus, this is called as the left hand derivative at a. Now if this left hand derivative and the right hand derivative are equal, that means both these limits are equal at x equal to a, then we say that f is differentiable. F is differentiable at x equal to a. So the fundamental definition of derivative is also linked with limits only. We have to understand that. That's why concept of limits is the most fundamental and basic. So function is said to be differentiable when left hand limit is equal to the right hand limit. Now, of of what? The slopes of the secants. So left hand derivative is equal to the right hand derivative. Now, and the limit value is denoted as f dash a, which is same as f dash of a plus will be same as f dash of a minus. Okay, this f dash of a, or we write as dy by dx at x equal to a, is called as the derivative. It's called as the derivative or differential coefficient of f at a, at x equal to a. All right. So this is the fundamental concept. If you look at this way, then you will never go wrong with the calculations of derivatives and functions, derivatives and differentiability at a point. So geometrical meaning. So suppose a function has a smooth curve at x equal to a. Okay, smooth curve at x equal to a. Then you will have a unique tangent. So unique tangent exists at x equal to a. All right. Therefore, f is differentiable at x equal to a. In contrast, let's say we have a function like this. There's also a function. It has a sharp corner. This is at x equal to a sharp corner or sharp edge. Sharp corner or sharp edge at x equal to a. All right. So function has a sharp corner or sharp edge. Now, there is no unique tangent. Why? Because you take at a, you take a point just left to a and draw a line. So that tangent will be like this. This will be one tangent to the left. Then take the point A, and just to the right of A, you take another point and you draw a tangent. It will be like this. Tangent at A plus. This is tangent at A minus. Okay. The sharp corner or edge. So whenever there are sharp corners or abrupt change in slope, then the function will not be differentiable. Function will not be differentiable at x equal to a. Whenever there are sharp corners, abrupt change in slope. Clear? So geometrically, this is the meaning of differentiability. If function is differentiable, there will be a smooth change in the slope. The curve will have smooth curvature. Whereas if there is a sharp corner, then there will not be a unique tangent, which means function is not differentiable. Right hand derivative will be slope of this tangent, and left hand derivative will be slope of this tangent. Okay, is it clear? Everyone, please respond.
Yes, sir.
Okay, so this is the geometrical meaning of derivatives. And if a function is differentiable, so if a function is differentiable, at x equal to a, then the slope of the tangent at x equal to a is called as the derivative of the function at x equal to a. Slope, derivative of a function is nothing but the slope of the tangent at that point. This we will use so much in application of derivatives. This concept is so important in application of derivatives. All right. So this is about differentiability. I hope it is absolutely clear. So you go through these notes. This is what I have explained here of sharp corners and this thing. Now differential coefficient at a point. Now the same derivative can be at a point can be written in this fashion. Like f of x be a real valued function defined for an open interval AB, defined on an open interval AB, and C belongs to AB. Then f is said to be differentiable or derivable at C if the limit f of x minus f of C by x minus C exists and is finite. So this is just another way of writing it. So I'll just show this. Another way of, instead of taking a plus h and a minus h, this is another way of representation. Now let's say this is a curve again, and this is the point C, and this point A has the coordinates C comma f of C, and we choose any arbitrary point B and we write in terms of the general variable. So B will be x comma f of x. So what is slope of AB? Slope of AB is f of x minus f of C by x minus C. Now, when we, so this is the chord AB, and we can extend this chord. We can extend this chord so it becomes a secant. Now, when we take the limit of this, limit as x approaches C. Now, x can approach C either from the left or from the right. So it doesn't matter. So both are taken. So f of x minus f of C by x minus C. So if this limit exists, that means left hand limit is equal to the right hand limit, which means the tangent from the tangent at A from the right and the tangent from A from the left will both coincide. There will be a same straight line. Then f dash C, which is the value of the limit, is the differential coefficient or the derivative of the function at C. That's what it means. Okay. So this limit is called the derivative or differential coefficient, and it has this notations. So the same thing, instead of a plus h, a minus h, we have written this way. Now, so this is another way of writing. Now, what to do next? This is differentiability on an interval. Differentiability on an interval. A function f of x is differentiable on AB if function is differentiable at each point in the interval and also at the endpoints. So a function is said to be differentiable on closed interval AB if at every intermediate point on the interval it is differentiable, and also at the endpoints. Now at the endpoints, how do we define? So at A, only the right hand derivative must exist. That means it should not be infinity, or you cannot, a function is undefined at that point. And then left hand limit at B, it should exist. Then we say function is a differentiable function. Function is a differentiable function. If it is differentiable at every point on the interval, then it is said to be a differentiable function. And a function is said to be a differentiable function if it is differentiable at every point of its domain. So this about differentiability. Now the important point, derivative of function at any point. This is what we deal with most of the time. Derivative of the function f of x at any point x. So far we said at A, at C, that's how we are discussing. Now at each and every point in the interval, now I want derivative of the function at any point. So we choose this fundamental derivative, go to the very first section that we discussed today. F of a plus h minus f of a by h, f of a minus h minus f of a by minus h as limit h tends to 0. So if a function is differentiable in its domain, then its derivative at any point is given by this fundamental value. F of limit h tends to 0, f of x minus h minus f of x by minus h, or limit f of x plus h minus f of x by h as x tends to 0, as h tends to 0. So the right hand derivative or the left hand derivative, both will be equal because it's a differentiable function. So this, when we don't write a here, in the previous case it was a minus h, we have replaced this a with a general variable x. We have replaced a with the general variable x, then, and we made h tend to 0, so we get f dash x, and this is how we get the value of all the derivatives of all the functions from this fundamental derivation, or we call it differentiation from first principles. All these formulas we obtain. What is that? Derivative of a constant is 0. So derivative of a constant is 0. Derivative of x power n is n x to the power n minus 1. Derivative of e power x is e power x. Derivative of a power x is a power x log a. Derivative of log x is 1 by x, and log mod x is also 1 by x. Derivative of log mod x to the base a is 1 by x by log a to the base e. Derivative of sin x is cos x. Derivative of cos x is minus sin x. Derivative of tan x is secant square x. Derivative of cot x is cosecant square x. This is a mistake here. This is cosecant square x. Cosecant square x. Derivative of secant x is secant x tan x. Derivative of cosecant x is minus cosecant x cot x. Derivative of sin inverse x is 1 by under root of 1 minus x square. Derivative of cos inverse x is minus 1 by under root of 1 minus x square. Derivative of tan inverse x is 1 upon 1 plus x square. Cot inverse x is minus 1 by 1 plus x square. Derivative of secant inverse x is 1 by mod x under root of x square minus 1. Derivative of cosecant inverse x is minus 1 by mod x into x square minus root x square minus 1. Now these all formulas have been derived from this expression, and these are standard. For example, we have done this. We have done this, right? Limit x tends to a f of x, sorry, x power n minus a power n by x minus a is what? N a to the power n minus 1. This is what? This is a derivative of which function? F of x is equal to x power n, where at x equal to a, as x tends to a. Okay, so that's the derivative of this function. So like that, so That's why derivative of x power n is n into x power n minus 1. So before I go into derivatives, now let us, so this is the basic formula. And for a gate, it is assumed that you know derivatives and you know how to differentiate. It is just assumed. There are no questions given directly on derivatives. They are given on application of derivatives. There are questions on continuity and differentiability, but not on derivatives. Application of derivatives are there. Derivatives, rarely some questions come, very, very simple. A few examples we will take. Now, let us go to class time. So I have a questionnaire, 8 questions on continuity differentiability. These are all previous GATE question papers. Now, let us start solving this one by one. So I'm starting the new session. You open classtime.com. So when you open classtime.com, you should get a window like this. So right now, open in your web browser, open classtime.com. Now I will start the new session. So oh, I'm sorry. I'll close this session. Proceed. So this is your activation code 95Y658. 95 capital Y 658. So go to classtime.com and enter your code here. 95 capital Y 658. Join. And enter your name. Okay. So I'll start releasing the questions. So everybody has joined. 12 members have joined. More to join. 95Y658. Classtime.com. Don't go to previous other logins and all. You just go to this. I will put all of you into a class. I'll put all your email IDs into a class. I'll create that class for you. How many more to join? One more to join. Okay, one more person to join. I don't know. 17 participants, so 2 more to join. Oh. Please join. I'm releasing the question now. 95Y658 is the session code. Okay, so first question has been released. So this is the question. The function f of x equal to modulus of x plus 1 on the interval -2, 0 is, options are these: continuous, differentiable, so take time. I am just giving 2 minutes time for you to solve the question. I'll open the timer. Please give your answer. Another 30 seconds. 1, 2, 3, 4, 5, 6, 7, 8. 8 more students to answer. Okay. So let's go to the question here. Now we should know, see, the graph of y equal to mod x, we have already discussed. Yeah. See, y equal to what you call modulus of x. So this is the graph. This is a graph of y equal to modulus of x. It has a sharp corner. It is continuous because you do not have to lift your pen to draw it. There is no gap. There is no gap. But it has a sharp corner at 0. In fact, the left hand derivative will be -1 and the right hand derivative will be +1, because see the tangent slope, tangent will be same as the function here, because it's a straight line already. Function is already a straight line. Slope of the curve just to the right is +1. Slope of the curve just to the left is -1. Now, see this curve x minus a. You just see here, when a is just see, when a is positive and a is negative. So a is positive, it is moving right. When a is negative, it is moving left. Okay, this is how it moves. Modulus of x minus a. Now what do we want? At function at a equal to -1. This is the graph. So it is modulus of x graph, but it is moving, it is shifted to the left by -1. That is modulus of x plus 1. This is the graph. So it will not be differentiable at x equal to -1. Now the given interval for us in the question is -2 to 0. So from -2 to 0, the function graph will just be this portion. let us plot. I'll copy this. Yeah. So this is the curve that we are dealing with. This is the curve. F of x equal to modulus of x plus 1. Now between -2 and 0. So this is the portion. Throughout it is continuous, but it is not differentiable at x equal to -1. So the answer is it is continuous on the interval, but not differentiable at all points. The other option is continuous and differentiable means it is throughout continuous and throughout differentiable. Wrong. And here it is neither continuous nor differentiable. No, it is continuous. It is differentiable but not continuous. So these options are wrong. Neither continuous, not continuous. These are wrong. So this is the correct answer. Is that clear? Very simple. Just I didn't do left hand derivative, right hand derivative. Just my idea of graph I have. If I want to show, I can show. Mathematically, I'll show this. One example I'll take. If I want to do mathematically, I want to check continuity. Now I don't have to worry about other places. I have to just worry about when this becomes 0. Now f of x is modulus of x plus 1. This becomes 0 at x equal to -1. So at this point, I need to verify. So left hand limit is limit x tends to -1 f of x. I'll simply write this as f of -1 minus. Okay, it means left hand limit. If it is dash f dash, it means left hand derivative. Okay, we will use these notations instead of writing this whole limit. So I'll get modulus of -1 plus 1, 0. Right hand limit, for this time I'm writing this. You get minus x plus 1, again 0. Left hand limit is right equal to right hand limit, and function value at -1 is 0. So left hand limit is equal to right hand limit is equal to function value at -1, which is equal to 0. So function will be continuous. Function will be continuous. Okay. But differentiability at that point. Now left hand derivative f dash of -1 minus is limit x tends to -1 minus or I will write it like this, h tending to 0, f of -1 minus h minus f of -1 by minus h. Okay, this is the left hand derivative. By first principles I'm doing, which is not required, but I'm just giving one example for you to do it. Now this is modulus of x plus 1. So this will be limit h tending to 0 modulus of -1 minus h plus 1 minus, what is f of -1? 0 by minus h. So we get limit h tending to 0, modulus of minus h by minus h. Now modulus of minus h is positive, minus h is negative. Modulus of negative is minus of that quantity. So we get positive h by negative h. The ratio h gets eliminated, you get minus 1. So left hand derivative is minus 1. Right hand derivative, limit h tending to 0, f of minus 1 plus h x plus 1 f of, I'm sorry, f of minus 1 plus h minus f of minus 1 upon h. This is limit h tending to 0, modulus of minus 1 plus h plus 1 minus 0 upon h. We get limit h tending to 0, modulus of h upon h, limit h tending to 0, it is h upon h, which will be equal to 1. So left hand derivative at minus 1 is not equal to the right hand derivative at minus 1. So f is not differentiable. This is from the first principles. You just keep solving from the first principles. However, if you know the graph, it's very, very simple. You can straightforward do this problem. Okay, graphically, just visualization, nothing else you need. You can straight away write the answer. All right. Okay. So how many answers correct? Let's verify. Look at the screen. So 7 students marked right. All right. So 6 students write continuous and wrote continuous and differentiable. Okay, 1 student wrote differentiable but not continuous. Remember, if a function is not continuous at a point, it cannot be differentiable because it already has a brick. It cannot have a unique tangent. All right. Differentiability means function is already continuous, but continuity does not imply differentiability. All right, let's move to the next question. So this answer is next question. So this question, just 1 minute time. This doesn't require much. I'm just setting time for 1 minute. Please go to class time and check. So attempt the question. Okay, let me see the answers. Why? It's simple. Few more students have to answer. Please answer. 1, 2. One more student to answer. Just oh, I'm sorry. I was muted. The answer to this is if a function is continuous at a point, then its first derivative may or may not exist. All right. The previous case is an example where here mod x, if you take mod x graph, the function is continuous at x equal to 0, but it is not differentiable. At mod of x plus 1, it is continuous at x equal to minus 1, but not differentiable at minus 1. Okay. So if a function is continuous at a point, it is not necessary that its derivative exists because it can have a sharp corner. All right. So next question we'll move on to. Okay. Now the third question. Look, go to the class time and check for the third question. Again, there's a problem that has already been done. I'll just give 1 minute time. Yeah, let me look at the answers. 1, 2, 3, 4, 5, 6, 7, 8. 8 more students. So you require more time. Okay, I'll give another half a minute. One more answer I have to get. Okay. All right. So let's see the question. So now again, this is talking about mod x. Okay. Y equal to mod x. Let us look at this. So there's the mod x graph. Now, so y equal to mod x for x less than 0. That means it is this portion of the graph. And y is equal to x for x greater than or equal to 0. It is same. So it is same as mod x graph. There's no difference. Question is just a little twisted. Y equal to mod x for x less than 0. So it is this. And y equal to x for x greater than 0. So it is this. So it is same as y equal to mod x graph. And mod x will be equal to x when x is greater than 0. So you get this. Now at x equal to 0, y is discontinuous? No. Y is not defined? No. You can remove. Now both y and dy by dx are discontinuous. Y is not discontinuous. So by negation, you can say dy by dx is discontinuous at x equal to 0. Now, dy by dx is what? Slope. So slope throughout, if you draw this function, so dy by dx for x less than 0 will be -1. That is the slope. The derivative is -1. In the previous problem we have done. For the right hand side, the derivative, which is the slope, throughout any point on the curve you touch, you will get +1. Okay. -1 and +1. So now this function, dy by dx function, I will write this function as f dash x. F dash x is a function which is -1 for x less than 0 and +1 for x greater than 0. So when I draw the graph for this function, if I have to draw the graph for this function, f dash x, so it will be +1 and for x greater than 0, and it will be -1 for x less than 0. So this is f dash x graph for this function. This is the graph of f dash x. So f dash x is discontinuous. Someone has asked, yeah, what is the difference between option 1 and option 2? So option 1 is talking about y. That is, it is the function itself being discontinuous. Option 2 is, option 2 is talking about the function itself being continuous or discontinuous. Option 1 is talking about the slope of the function being continuous or discontinuous. So slope is constant throughout. Slope of the tangent at any point here on the curve is -1. Slope of the tangent at any point here is +1. So the slope is discontinuous. So I hope it is clear. So let's see the analysis. So 10 students out of 18 have answered correctly. 10 out of 17. So you see, you have to clear your misconceptions. We are not able to answer because some concept is not clear. So what I'm trying to do with this problems is I'm trying to clear your concepts. Next, let us do fourth question. Okay, this will take time. I'll give you 3 minutes time. Okay, let us see answers. Okay, question 4. One, two, three. Okay. So I think one, one, two, three. Three more students to answer. Okay, just now look at this. The question may appear to be little confusing, but actually it is the same question being repeated. See, the modulus function is so important, so important. That question just is played around that. Yeah. Now, see, let us see. We know these graphs. See, we can eliminate by using these graphs. Y is equal to x square. This graph we know. So there's a graph, it's a parabola. Now it's a simple parabola. It's a smooth curve, continuous curve, and between -1 and 1, somewhere here -1 and 1, the function is a smooth curve. It is a differentiable function. Question is, it is not differentiable. Okay, it is differentiable function. Okay, so this is not the option to be marked. Y equal to x minus 1 is a straight line. It is continuous. Straight line is always continuous and differentiable. All right, remember, polynomials are generally differentiable. And this is also a constant. This is differentiable. So we are left with this. What is this function? Maximum of x and minus x. Let us go to GeoGebra and see this. I will delete all this. Okay, first I'll draw y equal to x. And next I will draw y equal to minus x. I'll change color. Okay, so y equal to x and y equal to minus x. So between -1 and 1 they've said, so we'll just take this graph. So these two lines we know. These are basic lines that we can plot. So this is the line y equal to x, and this is the line y equal to minus x. The question is maximum of x and minus x. So when you look at the x greater than 0, there's a graph that is this y equal to x graph is lying about this above y equal to minus x graph. So which is greater, which is larger? This is larger. Okay, and when we look for negative x in the negative x-axis, y equal to minus x graph lies above y equal to x graph. So values of my y equal to minus x are greater than y equal to x, because this will be negative. values, this will be positive values. So in effect, this graph, when you choose maximum of in both cases, all right, when we choose maximum of, it refers to this graph. Which is same as your modulus x graph. This function, which is written in a hidden way, is nothing but your modulus function. This function means the same as modulus function. Now this is continuous at x equal to 0, but not differentiable at x equal to 0. So in -1 to 1 at x equal to 0, this function is not differentiable. Is it clear?
Yes, sir.
Yeah.
Yes, sir.
So that was the trick. It is just a way of confusing, but that's the way maximum of functions are written. Now look at question 5. Okay, this is a little thought has to be given. I'll give 2.5 minutes time. Oh, I'm very sorry. So this function f of x is equal to modulus of x cube is equal to x cube when x is greater than 0 and is equal to minus x cube when x is less than 0. Okay. Now, a trick to do this is this. This first derivative, forget about 0. You don't look at 0. The first derivative is differentiate this. You get 3x square for x greater than 0. Don't write equal to 0 because we don't know. And when x is less than 0, it will be minus 3x square. Second derivative, it is 6x, x greater than 0, minus 6x for x less than 0. Third derivative, 6 for x greater than 0, minus 6 for x less than 0. Okay, I simply differentiated. I split the function into two parts and differentiated. Didn't worry about the boundary. Now I can check at the boundary when I put x equal to 0. See, this function is continuous. The question asked is whether function is continuous. Function is continuous. Why? Because for x tending to 0 minus, it is 0. For x tending to 0 minus, it is 0. For x tending to 0 plus, it is 0. And at function value, it is 0. So function is continuous. First derivative, f dash of 0 plus is 3 into 0 square, which is 0. F dash of 0 minus 3 into 0 square, which is 0. So left hand derivative is equal to the right hand derivative. So first derivative exists. Similarly, second derivative will exist. Again, because 6 into 0 minus 6 into 0. Third derivative will not exist because 6 and minus 6. So it is twice differentiable but not thrice. It is twice differentiable but not thrice. Okay, this is the easiest way to do it. Easiest way to do it. So we can, nothing further to do it. One more alternative I will give. If you know derivatives of a composite function within a function, all right, derivative of f of g of x is f dash of g of x into g dash x. This next tomorrow's class we'll discuss this, but if you know this, f of x is modulus of x the whole cube. Okay, now f dash f x will be 3 times modulus of x the whole square into derivative of modulus of x. Derivative of mod x is mod x by x. Why? Because it will be plus 1 when x is greater than 0 and it will be minus 1 when x is less than 0, the derivative. So this way also you can think of doing it. All right. So or x by mod x. Second derivative also you can take this way, and third derivative also you can take it this way, or I can write I will write within the bracket plus or minus 1. Plus 1 for x positive, minus 1 for x negative. Okay. So that I keep reducing. Next is second derivative, 3 modulus of x square into mod x by x again. This will be plus straight away. Plus 1 minus 1, so it will be plus. I'll get modulus of 6. Sorry, 6x, not x squared. Now f triple dash six derivative of mod x is mod x by x. This will be 6 into 1 and 6 into minus 1. So third derivative does not exist. Okay. The easiest way is what I have explained here without any confusion. If you have a mod, split between left and right, and then you can do it. So this is the answer. Just 3 more questions short. We'll quickly finish. Okay, question 6. Which one of the following functions is continuous at x equal to 3? Okay, I'll give another minute time. Two minutes. Oh, why is it come like this? For x greater than 3, x less than 3. Yeah, the fourth option, yeah, it is not defined at 3. Nothing is mentioned. So which one of the following functions is continuous at x equal to 3? See, rule out by options. So look at the solution now. See, for this second option, see here, f of 3 is 4. And when x is not equal to 3, that is f of 3 minus and f of 3, sorry, not f dash, f of 3 plus. This is equal to 8 minus 3, which is 5. So left hand limit is equal to right hand limit, but it is not equal to function value. So this is discontinuous. Next, for x less than or equal to 3, so f of 3 minus is equal to f of 3, which is 6, and f of 3 plus is 3 minus 4, which is minus 1. So left hand limit is not equal to right hand limit. So it is a discontinuous function. And here at x equal to 3, the function itself is not defined. So discontinuous function. Look at this. F of 2, sorry, f of 3 is equal to 2. Now f of 3 plus is x minus 1. So 3 minus 1 is equal to 2. F of 3 minus is 3 plus 3 by 3, which is 2. So function value right hand limit and left hand limit are equal. So this is the correct option. Okay, this is the correct option. A is the correct option. Okay. Okay, next question. This is simple. You should be able to do it in a minute's time after we did so many problems. Let's see in a minute's time how many answered. Few. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Please answer quickly. I'll give another half a minute. Very simple. Very simple. Now this function, see, it's like modulus, it is a modulus function. So whenever the expression within the mod becomes 0, that is where it is critical. 2 minus 3x, where is it 0? When x is equal to 2 by 3. Other than that, so to the right side of 2 by 3 and the left side of 2 by 3, the function will change. Okay, that's all. Otherwise, it's a modulus function. Okay, it will modulus of, what's it? 3 minus 2x, 2 minus 3x, 2 minus 3x. This will be the graph. So at 2 by 3, it will be 0. And to the right and left, it will always be positive. So it will be a graph like this. Okay. So it is continuous and differentiable on all R? No. It is continuous on all R, correct, but not differentiable at x equal to 2 by 3. So this is the correct option. C is the correct option. Just by understanding, graphical understanding, you can do this right. Okay, the last question for today. These are all previous year's GATE questions, by the way. So timer, 2 minutes. Okay, look at the solution. Let us see how many correct. Again, yeah, good. This time many correct. Many correct. So look at the solution now. See, this is as we are talking about whether function is continuous. So left hand limit should be equal to right hand limit is equal to the function value. Function value at x equal to pi by 2 is 1. Now this is lambda cos x by pi by 2 minus x for x not equal to pi by 2. So for x not equal to pi by 2, I can write this as lambda into sine of pi by 2 minus x, all right, for x not equal to pi by 2 and equal to 1 for x equal to pi by 2. Sorry, divided by pi by 2 minus x, and this is equal to 1 when x equal to pi by 2. So this is sine capital X by capital X as x tends to 0. That is what it is. So this is limit x tends to pi by 2 lambda times sine pi by 2 minus x upon pi by 2 minus x. If you replace y as pi by 2 minus x, then as x tends to pi by 2, y tends to 0. So we have limit y tending to 0 lambda sine y upon y, which is lambda times 1. Sine y by y is 1. So limit of the function as x tends to pi by 2 is lambda, and function value at pi by 2 is 1. So for continuity, what should happen? The limit should be equal to the function value. So lambda should be equal to 1. That is the answer. So lambda should be equal to 1. So that's how we solve. All right. Okay. So give your ratings. Now, so you see in calculus, this is a tricky part, understanding of functions and how they behave. It's all about that, continuity and differentiability, but this forms the basis for application of derivatives, which is extremely important. All right. So I'll be sharing these notes. Those of you who made mistakes, who could not answer correctly, you please go through. Some of you have got full correct, very good. So if you have not got things correct, then there is some conceptual error. So you should go through the concepts. Okay. They are rare questions on GATE on this, but they are simple questions. But little, you just have to have a little practice. I'll share a practice assignment with you tomorrow. All right, for today's class, I'll end. If you have any doubts, you can raise.